Okay, now we're going to talk about quadratic models in 5.2. So this graph shows the stopping distance in meters and the speed of a car in kilometers per hour. Okay, describe the relationship between stopping and distance. Well, if we take a look at the graph, as the speed increases, the distance that it takes in order to stop the vehicle also increases. So as the speed increases, I'm going to do this for increases. The distance increases. Here we go. Okay. Use the graph to estimate the stopping distance at 50 kilometers per hour and at 100 kilometers per hour. Okay. So at 50 kilometers per hour, and then 100 kilometers per hour. Okay. So at 50, we want to locate 50. So this is 40, this is 60. So between it would be 50. So this is interpolation. You need 10 meters to stop. Distance. 10 meters of a distance to stop if you're driving at 50 kilometers an hour, and then 100 kilometers an hour. It's about right here. So this is 30, this would be 35. Let's go 37. 37 meters of a distance. Okay? So now the question is, if the speed doubles, I'm just going to change the color. If the speed doubles, does the stopping distance double? If not, describe the change in the stopping distance when the speed doubles. Okay? So if we're looking from 50 to 100, okay, that's what we just located. We located 50 here and then 100 here. Okay, so obviously this is a double. Okay, so what we would have to do is, like, at 50 it would be 10, but then at 100 it goes up to like 37. So this is not doubled. Okay, so it's not just 10 to 20 or 50 to 100 or 80 to 160. Okay, so the faster a car is going, we know from like 10 to 37, so this is like times 3.7. Okay, so it's not times 2. A double would be times 2. This is even more. So the faster a car is going, the more distance it needs to stop. And I'm going to scroll down. Okay, so consider the rate of change of stopping distance with respect to speed. What are appropriate units for the rate of change? Well, stopping distance, we know that it's going to be the change in y over the change in x, right? So if we go up here, it's going to be appropriate to do like the distance over the speed. So if we're actually going to talk about just the units, then it's meters per kilometers per hour. Okay, so a little awkward, but that's what it would be. Okay, is the rate of change of stopping distance with respect to speed increasing, constant, or decreasing? Okay, so it's definitely increasing because we can see this right here. This is a growth. Okay, so I know that we're talking about quadratic models. So this is either quadratic, where it goes like this, and we're only talking about the right-hand side, or it's exponential. So it doesn't increase like a line, but it increases at a non-constant rate. Okay, the table shows the distance and time for a free fall at an amusement park. Okay, so maybe a ride. Okay, so we have the time here and we have the distance here. So what we're going to do is we're going to calculate first and second differences. Okay, so just remember for the first differences, we're going up the y-axis. No. Okay, so we're going to subtract these numbers like this. So 33.6 minus 28.8. Okay, 28.8 minus 24.2. I'm not going to write all that out, but what we're going to get is 4.8, 4.6, 4.2, 3.8, 3.4, 3, 2.6, 2.2, 1.8, 1.4, 1, or 1.0, 3.0, doesn't matter, 0.6, 0.2. Okay, once you get up to 0.2, this is actually decimal 2 minus 0. For first differences, there's always going to be a box that's not filled in. Okay, and now second differences, okay, we're going to go up again. And then this time, there's not going to be, again, a box that's not filled in. So the second difference is there's actually 2 boxes not filled in. Okay, so if you go up this column and you see the differences of the first differences, what we notice is that these ones are the same. Okay, so if you go up, we're going to get 0.4 for every single answer here. Okay, so what does that mean? Okay, does the time column show equal time intervals? Okay, so time column is this one right here. Yes, they go up by 0.2 seconds each. Okay, does the distance column seem to be a linear relation? Okay, so distance column is right here. No, because they don't go up by the same amount every single time, right? Let's say the first differences are not constant. Okay, so by subtracting the distance column, we're getting these numbers here, and these numbers aren't the same, so it's not a line. Okay, so calculate the first and second differences. We've already done that. Do the differences imply an increasing, decreasing, or constant rate? Okay, rate of change of distance with respect to time. So right here, so first, okay, so second differences are constant. But since it's positive and it's not linear, so non-linear, it's not a line, it's increasing. Right. Okay, and does the table of value imply that it's linear or quadratic? Okay, definitely quadratic. And the reason is the second differences are constant. Okay, as a review, the first differences are constant, we have a line. If the second differences are constant, then we have a quadratic. So the first differences of a table of values are constant, then the model is linear. And if the second differences are constant, then the model is quadratic.